So electric current we've talked about in the past. Electric current is the direction that positive charge flows. But we also know today that positive charge doesn't move in a conductor. It's the negative charge that moves. It's the electrons. So why do we define current as the direction of positive charge moving when positive charges don't move? Well, in the past, we didn't know what charges moved. We didn't know what was going on inside a conductor. We just knew that it looked like positive charge might flow in one direction or negative charge might flow in the opposite direction. It would give you the same result. And we assumed, because of the way that Benjamin Franklin defined positive and negative charge, that the positive charge, the protons, were given a positive charge, the electrons were given a negative charge. So if you had a time machine and you were a physicist, one of the things you might want to do is go back in time, grab Ben Franklin and have him switch those conventions. It would make life a lot easier for people who are studying electricity and electric circuits. But how do we know that it's the electrons that are moving? How do we know today it's the electrons that are moving? Well, there's a simple effect, a simple experiment called the Hall effect that allows us to determine, is it the positive charges that are moving in a conductor or is it the negative charges that are moving in a conductor? So, Hall effect is the experiment that determines which charges are the ones that move. So we're going to look at here, in black here, is going to be a conductor. So think of it like a receipt you might get at CVS, 10 feet long for one purchase. But imagine instead of paper, it were made of copper. And on one end, you hooked a battery. On the other end, you hooked a battery. So you had current flowing through that copper sheet, the copper receipt. And I'm going to have the current going down. So some positive potential up here, flowing down to some negative potential below. So either positive charges in this copper sheet are moving downward, or the negative charges are moving upward. Both will give you a current going down, right? Because again, I is the direction where positive charges flow, which is opposite the direction that the negative charges would flow. So which is right? Which is the positive charge moving or is the negative charge moving? Well, Hall had a brilliant idea, and he took this copper sheet, this copper receipt, if you will, this long, thin copper conductor of length with L, and he put it in a magnetic field, shown here by the red. I think your book has the magnetic field coming out of the board. Here I have the magnetic field going into the board. The analysis is going to be very similar. I'll talk you through this version. So, if the positive charges are the ones that are moving, right, as the current goes down, those positive charges move through this magnetic field. When charges move through a magnetic field, they experience a magnetic force. Well, what direction? Well, fingers in the direction of the velocity of the particle. Push that velocity onto the magnetic field, which is into the board. So pushing that velocity into the board. Thumb is in the direction of the force of a positive charge. So these positive charges will experience a force to the right. So what will happen is as these positive charges flow down, they'll be pushed to the right of the conductor. So the right of the conductor will be positively charged, which means the left of the conductor has to be negatively charged. So all you do is have to take a voltmeter, touch the two sides, and see, does this side have a higher potential than that side? Does the right side have a higher positive potential than the left side does? If it does, the positive charge carriers are probably the ones that are moving. Well, how do we know that? Well, let's see what happens with the negative charge carriers. Negative charge carriers are moving upward. Again, right-hand rule. Fingers in the direction of the velocity. Velocity is going up. Push the velocity out of the magnetic field. The thumb is in the direction the positive charges would experience a force. This is a negative charge, so we flip the direction. So the negative charge would experience a force to the right if it were moving upward, which means that the negative charges would build up on the right-hand side, and the positive charges would then build up on the left. Exactly the opposite of what would happen if it's the positive charges that are moving. So this is a wonderful definitive experiment. The right side of this experiment will have a higher potential than the left if it's the positive charges that are moving. The left-hand side of this experiment of the sheet of copper will have a higher potential than the right if it's the electrons that are moving. You can set up a voltmeter, take those measurements, and definitively show it is actually the electrons that are flowing, not the protons. Well, what is that potential, this EMF, on either side of the sheet, setting up the potential? How big is that potential? Well, the equation your book gives is the potential across this sheet, not from top to bottom, which also has to have a potential for current to flow, but from the left to the right. Because of the moving charges, the potential between the left and the right, here the left will have a higher potential than the right. How much higher? It depends on the strength of the magnetic field, because the stronger the magnetic field, the stronger the magnetic force, and the more the negative charges are going to be pushed to the right. So you have more negative charge on the right, less negative charge or more positive charge on the left, which will give you a bigger voltage. It depends on the width of the sheet, and it depends on how fast these electrons are moving, these charges are moving. So the Hall effect potential across the conductor depends on the magnetic field strength, the width of the conductor, and the speed of the charges. And remember, the speed of the charges is usually very, very slow. So this experiment, this Hall effect, proved definitively that it was the electrons that move in a conductor, not the protons. However, even though we know it's the electrons moving, we still define the current as the direction of the positive charges. If the positive charges moved, which direction would they move? They move opposite the negative charges. So we still define current, even though we know the positive charges aren't the ones that are moving in a conductor, like a copper wire. We still define current as the direction the positive charges would move. And then conversely, it's the opposite of the direction that the electrons actually move.